Yeah, so that actually worked out well. Okay, so that's where we were when we left yesterday. All right, cool. All right, so we just got to take an integral of this mess. So first of all, I'm going to clean this up a little bit, right? I got x times 0.125x. So that's going to give me the integral from 0 to 0.75 of 0.125x squared dx over the integral from 0 to 0.75 0.125x dx. Right. So don't get too freaked out. It's like, I've got an integral and a fraction. Just take the two integrals one at a time. Okay? So what do I have to take the derivative of so that I get x squared? X cubed, but then over 3, right? So that top integral is going to be 0.125 over 3 times x cubed, right? And to this day, this is still how I take integrals. I just think, what do I have to take the derivative of to get that thing? So here, when I multiply by 3, the 3's cancel, and I get that, right? Okay, and I want to do that from 0 to 0.75. Oops, 75. All right, and then on the bottom, what am I going to get? Let's see, the bottom one. What do I have to take the derivative of to get 0.125x? 0.125 over 2x squared from 0 to 0.75, right? Follow? And so now just simplify. Like put in 0.75 and put in 0 and subtract it out. Okay? Now, there are some tricks you can do here because I've got the same bounds. So you can actually simplify this. X's cancel, the 0.125's cancel. So I'm going to take a quick shortcut here. You are welcome to go through and do it. You know, put in 0.75, put in 0, subtract. Put in 0.75, put in 0, subtract, and then divide. And that will work. But because you've got the same bounds, and there's no addition or subtraction or anything here, even if there was, would it matter? No, I don't think it would matter. It wouldn't. So the 0.125's canceled. You end up getting 2/3 of x between 0 and 0.75. X squared's canceled, so you get x. 1.25's canceled, and the 2 flips up to the top. Okay, and then just now plug in your numbers. Let's see. 2/3 of 0.75 is 0.5. 2/3 of 0 is 0. 0.5 minus 0 is 0.5. And the units are meters, right? Because we're talking about a position.
So what is that?
So, good question. So we just spent like a class and a half trying to figure out this stupid thing. What is the stupid thing we just found? It's the center of mass. It's the x-coordinate of the center of mass. All right. Now, if you wanted to, here's, I don't know if this will help you shed any light on this, but so remember, our linear density was this, 0.125x, right? So if you were to graph that, it would just be a kind of a straight line, right? With a slope of 0.125, right? So this is telling me that, so here's 0.25, 0.5, 0.75. This is telling me that my center of mass is right there. 0.25, 0.5, 0.75. Which kind of makes sense, right? It's closer to the heavy end, right? Cool. So it turns out, well, okay. Good. All right. There were not any of these in your book. I wrote one problem like this and put it on your homework. I think it's number 7 on the first homework assignment. Please do it. Okay, let me double check that number. Is it number 7? It says this is not in the book in parentheses. Great. Yeah. I haven't been. I tried that early on and I abandoned it because it wasn't doing what I hoped it would do. And I mean, ultimately, I can't show you everything, but the more problems you do, the better prepared you're going to be. So really, you should be doing all of them. All right, are we good, you guys? Okay. Now, when you do number 7 in the homework, it's the exact same method. Okay? The only difference, and it sounds like it's going to be way harder, but I swear to you it's not. The only difference is the one in the homework is instead of it being 0.125x, it's whatever, 0.125x squared. But it doesn't make it any harder. PT squared. Okay? All right. Questions? Okay. All right. Now, Newton's second law. Can I skip a page? I remember my slides were out of order. I fixed it. Okay, cool. All right. So, remember yesterday we talked about throwing the hammer and we said that the center of mass would just follow a nice path? Okay. The idea is the center of mass follows the exact same path that a particle located at that position would. Okay? So it turns out that we can kind of use Newton's second law and apply it to a system of objects. Okay? So if you have a system of objects, where they've got two particles, and I find the net force on that system, okay, the center of mass of that system will follow Newton's second law. In other words, net force equals mass times acceleration. Okay? Now, when you find your net force, this is important. Your net force is the sum of all external forces. You guys remember talking about external forces when we did systems before? Okay, so if your system consists of these two objects pushing each other doesn't matter, right? Because that would be an internal force. Okay? So the only way that the motion of the center of mass will change is if some force comes from outside my system and affects one or both of the objects. Follow? Okay? So, I think that's probably most easily seen by doing an example. So that's kind of where we're headed here, all right? But just a couple comments about the notation. First of all, remember, when you do your net force, it's only the external forces that count. The book uses this notation more than I do, but when you see it in the notes, capital M just means the total mass of the system, the mass of all of your things added up. And then ACOM is obviously the acceleration, not of the objects, but the acceleration of the center of mass, which is weird, right? So I think before we can go any further, we got to talk for a minute about velocity of the center of mass. All right? So we just talked about position of the center of mass, right? So how do we find the velocity of the center of mass? So, in other words, suppose we've got two particles with equal mass. Where would the center of mass of these two things be? Right in the middle, right? Okay, now, if the two objects are moving, then so is the center of mass, right? Okay, so we need to find a way to figure out how the center of mass is moving. Follow? But it turns out that it's not that level. I think this basically just says what I just said before. I'm going to come back to this page. Let me do an example and then we'll come back to it, okay? Where is it? Sorry, I know I'm jumping way ahead. All right, so I jumped. This is like 2 or 3 slides ahead. I apologize. I'm going a little out of order here. Everybody see where I'm at? Okay. So, how do we find the velocity of the center of mass? Well, look, this is the equation for the position of the center of mass, right? And what's the relationship between position and velocity? If you have the position, how do you find the velocity? Take the derivative, right? So if I differentiate this with respect to t, we just end up getting dx1 dt, which is the velocity of object 1. dx2 dt is the velocity of object 2. So it's the exact same equation, except use velocity instead of position. Okay? All right, so this is how you find the velocity of the center of mass. All right? And so the idea is this center of mass will follow Newton's laws. So if there's a net force that produces acceleration, that acceleration will affect this velocity. Okay? All right, so let me do what I think is, yes, the next example here. So let me do this example so you can kind of see it with numbers. All right? And then we'll go back and we'll talk about some of the concept-y stuff that I just skipped over, and I have a real quick demo to show you. And then if there's time, I have, well, getting ahead of this. Okay, so Here we go. So we got a 1,000 kilogram automobile, which is at rest at a traffic signal. At the instant the light turns green, the automobile starts to move with a constant acceleration of 4 meters per second squared. At the same instant, a 2,000 kilogram truck traveling at a constant speed of 8 meters a second overtakes and passes the automobile. So at the beginning of the problem, both objects are at the same location. Okay? The automobile is going to start to rest and go and speed up, right? And at that exact same instant, the truck is already moving. Follow? Okay? So, based on that, we need to figure out these questions. Okay? So, we kind of need to keep track of information about the two things. So I'll refer to auto as an automobile and truck as in truck. All right, so here we go. So for the automobile, here are the things we know. We know that it has a mass of 1,000 kilograms. I know that it starts at rest. All the A's just mean auto. I know it's going to accelerate, so the acceleration of the auto is 4.0 meters a second squared. And all of this is occurring at, at the same time. Okay, so over here, the truck. So, at the same instant, truck. So here's the mass of the truck, 2,000 kilograms. Traveling at a constant speed. So the velocity of the truck is, what did we just say, 8 meters a second. And I'm just going to put in parentheses constant so that I remember that that guy's not changing. All right. So at time 0, both the automobile and the truck are at the same linear position. So my center of mass at that point would be 0, right? Follow? Okay. So question A says, how far is the center of mass of the automobile truck system from the traffic light at 3 seconds? Okay, well, so we're looking for the position of our center of mass. So basically, I'm going to find the position of the automobile, the position of the truck, and then use that equation that we just looked at, right?
Wait, is this two-dimensional?
So top view, here's the road. So here's the truck, and here's the car.
That's
yeah.
So that's a copy, one-dimensional?
Well, I mean, they can't be on top of each other.
That's what I'm saying.
Yeah, so, yeah, this hadn't occurred to me. Yeah, I mean, you're just sort of,
Okay.
you're worried about where the center of mass is this way. You're right. Top to bottom, the center of mass is going to be a little closer to the truck.
Yeah.
Because the truck has more mass.
Okay.
Good.
Okay.
So you should sort of be treating them as particles that are traveling along the straight line. So they can, in essence, sort of travel through one another, which I know isn't possible.
Yeah.
But so this is a book problem, and they've oversimplified that aspect of it.
Okay.
And that didn't occur to me until like the second before you were asking it.
Yeah.
All right, but you guys, are we good? We're just assuming this is all taking place on a straight number line. And we're not worried about the fact that technically the truck is here and the car is sort of next to it. Good? Okay, cool. All right, so to find these, well, this is constant acceleration, right? So my position here is going to be 1/2 AT squared plus VOT, right? Does that make sense? Okay, so let's see, we're going to get 1/2 times 4 times, oh, what's our time? I forgot to write down the time. 3 seconds. So T equals 3 seconds. So times 3 squared, so 3 squared is 9 times 2, so we're going to get 18 meters. So that's the position of the auto. Follow? Okay, now let's do the same thing for the truck. Do I need to use this equation to find the position for the truck? No, it's got a constant velocity, right? So position for the truck is just going to be, oh, well, it's traveling at 8 meters a second. For 3 seconds, it's going to go 24 meters, right? Follow? So now, after 3 seconds, I know where the automobile is and I know where the truck is. The automobile has a position of 18 meters. Truck has a position of 24 meters. So now I can find my center of mass. So that should be the position of the auto times the mass of the auto plus the position of the truck times the mass of the truck all over the total mass of the auto plus the mass of the truck. And plug in your numbers. So, before we calculate it, should my position, well, first of all, give me a window. What two numbers does the position of my center of mass have to be between? It's got to be between 18 and 24, right? Closer to 24 or closer to 18?
24.
Closer to 24 because the truck has more mass, right? So we're going to get 18 times 1,000 plus 24 times 2,000, all divided by 3,000. Figure it out, and you end up getting 22 meters. All right, so that was not super enlightening, but it was a simple finding the center mass calculation. Parts B and C will be a little bit more enlightening, and I'll connect it with what I was just saying about Newton's laws. So before I do other questions, also, real quick, your smiley face didn't land where it was supposed to, so I apologize on your notes. Your smiley face is sort of in the middle of your workspace. I reformatted it and forgot to move the picture. All right, so let's. Oh, darn it. Undo. No, it wasn't erasing. I was trying to highlight. There we go. Seriously? Forget it. All right. Okay, so question B. Question B, what does it say? At this moment, what's the velocity of the center of mass? All right, so I'm going to do this two different ways. All right? The first way I'm going to do it is, so we're trying to find the velocity of the center of mass at t equals 3 seconds, right? So, solution number one. Well, solution number one is to use the equation I just gave you. The velocity of the center of mass is equal to the mass of the auto times the velocity of the auto plus the mass of the truck times the velocity of the truck over the total mass. What do I have to do before I can use that? Find those two velocities, right? So let's see. After 3 seconds, the velocity of the auto is going to be, well, our VI was 0, and then we accelerated at 4 meters a second squared for 3 seconds, so that's going to give us 12 meters a second, right? Did I do that too fast? Or? Okay. What's the velocity of the truck after 3 seconds? 8 meters a second, because it's constant. So let's plug in our numbers. So the mass of the auto is 1,000. Velocity of the auto is 12 meters a second. Plus the mass of the truck, 2,000. Velocity of the truck is 8. Is this all right? I'm worried I mixed up my truck and my car. Are we good? Okay. I had this all written down. I suppose I could put my notes out. All right, divided by 3,000 kilograms. And it gives you 9.3 repeating, if you want to keep track, meters per second. Yes.
So it's not that. What's like the application for like finding center mass, like car and like two things moving? What's like the application?
So it wouldn't make sense for this scenario to do that. In a minute, I'm going to show you an example of like a real life scenario where it might make sense to talk about that.
Okay.
This was good because I wanted something where the two objects had different velocities relative to each other, and I wanted something that was a little
That
bit.
makes sense, yeah.
So we'll get there. That's in the back of my head. So we're in a fair question. All right. Is everybody okay with what we've done here? All right. Now, the second solution doesn't make a ton of sense. Let me say that wrong. Or let me say that again. The second solution you probably wouldn't use. Like, this is the best solution for this problem. Okay? But I think that there's some value in showing you the second solution because it shows you what I was talking about Newton's laws. All right? So let's do this. Solution number 2. All right, so let's do this. Let's find the initial velocity at the center of mass. This is going somewhere. Let's find the initial velocity of the center of mass. All right, well, that would be the mass of the car, which is 1,000 kilograms, times the initial velocity of the car. What was the initial velocity of the car? 0, right? Plus the mass of the truck, 2,000 kilograms, times its initial velocity. What was that again? 8 meters a second. Divide that by our total mass of 3,000 kilograms. So that means that our initial velocity is, if you figure this out, it gives you 5.3 meters a second. Good. Okay. Now let's think about forces. So in this problem, there are two objects. There's the car. I don't know how to draw a top view of a car. For whatever reason, I feel like the car should be more rounded. So here's the car. Here's the truck. You look like an eyeball. All right. So what's the net force on the truck? 0. How do you know the net force on the truck is 0? Yeah, the velocity's constant, right? All right. How about the net? Oh, I'm sorry. I should be saying auto, not car, right? There. I'll put wheels on it and then. Okay. So, how about the net force on the auto? Be mass times acceleration, right? So the mass of the auto was 1,000 kilograms. The acceleration of the auto was 4 meters a second squared, so we got 4,000 newtons. So what's pushing the auto forward? Like what is that force? Friction, right? That's the force of friction. Is that an internal or an external force? External force. So are there any other forces that are going to affect the motion of either of these two objects?
Drag force.
Yeah.
No, that must be taken into account because this is a net force. So you're right. So this technically is friction minus drag force, blah, 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 right? So I've already taken into account all the forces, right? So let's do this. So what's the net force on the system? Well, there's only one external force. It's 4,000 newtons, right? Follow? That means that I can find the acceleration of the system, which is the same as the acceleration of the center of mass. So to find the acceleration of the system, I'm going to take the net force of the system and divide it by the mass of the system. You guys all know what I mean when I say system? We're talking about the truck and the car, right? Or the auto and the truck. So the mass of the system is 3,000 kilograms. Divide it out, and you get 1.3 meters a second squared, right? All right. Now, is there any one object in my problem that's accelerating at that rate? No. That's the acceleration of the center of mass, right? Because as the auto speeds up, they're getting sort of farther apart, or well, whatever. Your sort of overall velocity is increasing, and as a result, the center of mass is accelerating. So, check it out. V equals VO plus AT. What was our starting velocity for our center of mass? We calculated it before. Oh, well, that doesn't help at all. But yeah, it was 5.3 repeating, right? Sorry, we're almost done with this example. So 5.3 meters a second plus the acceleration of our system is 1.3 meters a second squared. What was our time? 3 seconds. What's 1.3 repeating times 3? 4 plus 5.3 gives 9.3. Why am I happy? It's the same thing we got before. Right? So David's totally right. This is stupid. You'd never do this with a problem like this. All right? But it illustrates the fact that even if you have two totally seemingly unrelated objects, they still, if you treat them as one system, they still obey Newton's laws in exactly the way that you would anticipate. Follow? That's why when you throw the hammer, it seems to be spinning around, but the center of mass follows that nice parabolic path. It's the exact same thing. Good? All right, so why the hell do we care? So, imagine a billiard ball. Imagine a billiard ball moving towards another billiard ball, right? This guy has an initial velocity of 0. For simplicity, let's say that this has an initial velocity of, whatever, 4 meters a second, right? So that means that the center of mass is moving this way, right?
Yes.
After they collide, there are forces, but they're internal forces, right?
Yes.
So even after the two pool balls collide, that center of mass still has to keep going in a straight line. Okay? So if one ball ends up going that way, the other one has to go that way. When we do momentum, which is sort of where we're headed, that's all that's happening there. You're just conserving your momentum so that your center of mass continues along a straight path.
Wait, so the center of mass would stay in the straight line?
Correct. Because all of your forces are internal, right? It's the cue ball hitting the 8 ball, right? And if your system is the cue ball and the 8 ball, then the collision between them is only internal forces.
Okay. That makes sense.
Good?
Yeah.
Right? Because it's object A pushes B, B pushes A. If my system is objects A and B, then everything's internal. Okay?
Does that mean we could do a problem like with two pool balls like that? You did that, and they collided, and you gave us like how fast and the angle like one of them was going. You could find the other one, knowing like. Where
Exactly. And that's where we're headed. We're going to be doing problems like that. Did I cut you off?
No.
Okay. All right. Are we good with this?
Yeah.
All right. So here's a real simple example. So I've got 2 carts here, and I attached them by means of a spring. I'm trying to figure out a way to do this with a motor, but I was happier before that happened. All right. So anyway, unfortunately we got to use a spring. All right. So the way they're set up right now, this cart has a mass that's twice as big as this mass. 1 kilogram, half a kilogram. Okay? All right, so what I'm going to do is I'm going to stretch them apart, and I'm going to set them so that this cart right now, the front of the cart is at 100 centimeters, and this cart's at 160 centimeters. Okay? They're both pulling each other, correct?
Yeah.
Cart A is pulling cart B is pulling cart A. Are there any external forces? Gravity, normal force, but are those aren't going to affect our motion at all, right? So everything here is an internal force, right? Basically, the spring is allowing the 2 carts to pull each other, right? So what's the velocity of my center of mass right now?
That's right.
0. Where do you think the center of mass is if this one has twice as much mass as this? Over here, right? It turns out that it's a third of the way in. It's at 20. Okay, and this is at 60. All right? So the velocity of my center of mass is 0. So and the center of mass is right here at 120. Right? There. So that little mass that I just set up, that map marks where the center of mass is. Where do you think they should collide? Right there, right? Because there's no external forces. My center of mass has to not move, right? What? Okay.
Oh my God.
All right. So that's a scenario where you might actually talk about it. Okay. Good. All right. So yesterday, unfortunately, it's not here. Yesterday, Patrick's in my tutorial, and I pulled out those little green rolly carts. We both sat on carts, and my goal was to have him pull me, and we would meet in the middle like this. But unfortunately, the rolly carts had too much friction, so it didn't work very well. But so let's rewind. We skipped some problems here. So read this guy, checkpoint 2. It's back a page or 2 in your notes. It's basically exactly what you just saw.
Never ever will there be a speeder named Ethel.
Oh.
Yeah, my grandma's out skating with her fucking friend.
My grandma's name's that. All right, where are they going to meet, you guys?
center.
Right? Well, not in the center, at the center of mass, right? Does that make sense? Doesn't matter who does the pulling.
No.
No, because of Newton's third law, right? If Ethel pulls Fred, then Fred pulls Ethel, even if one of them isn't, sort of physically pulling, right? Because that's what Newton's third law says. Good? All right, so jump back one more slide. All right, so we talked about the billiard collision, right?
Yeah.
We talked about, they used a baseball bat here, but like if you throw a hammer or a baseball bat or a bowling pin, the center of mass follows a nice parabolic trajectory. All right, fireworks. You guys have all been to see fireworks. I'll give you an example, if you know what fireworks are, right? So the idea is, there's a little launcher, right? It shoots this projectile up into the air, right? And then when it gets to some point in its path, it explodes, right? Some of the particles go that way, some of the particles go that way, but that's all internal forces, right? That's the particles pushing each other. So if you averaged up the position of all those particles, it would just continue the parabola, the parabolic path.
Really?
Wow.
Okay? If you, next time you go to the, so it doesn't work perfectly because unfortunately after it explodes, the air resistance increases, right? Because now your particles are much smaller, there's some dissipation of energy, but if you watch, the sort of the cluster that is, your explosion, it falls, it moves down in the sky a little bit, okay? Because gravity is pulling all of those particles. That's why you get that curved path, right? Okay?
So like even though if you fire at like a 45-degree angle, even though there are particles that like fire back at you, they'll still be technically going the other way a little bit.
Well, no, and there's a problem on the homework that deals with exactly this. Let's do it.
Oh, okay.
What did you just say?
I just said that, like, since it's the center of all of it, so like when one goes back, at the same time the other one's going the other way, so they kind of cancel out.
Exactly, yeah. So let's suppose that it happens right at the top of the path, right? So you get to the top of the path. Right now your overall velocity is that way, right? So the idea is, if it explodes at the top of the path, maybe one piece goes flying forward. That's going to now be moving forward faster than it was before, right? Because it was already moving forward and it got pushed forward, right? That means a particle that got pushed backwards is either going to be moving backwards or at the very least moving forward slower than it was before, right? But overall, your center of mass is going to follow that same path. Good? Questions? Alrighty. I think we hit everything that we need to.
Yeah.
I think that's it. All right, I thought it would be worthwhile to do one other. Most of the problems here seem to be about center of mass. There's a little bit about velocity, center of mass. Yes, the definite emphasis is on, did I say that right? The emphasis is on center of mass, not the velocity of center of mass. Okay? So, I'm going to give you guys a problem. I want you guys to see if you can figure this out for me, all right? So I've got a meter stick here. The meter stick has a mass of 70 grams. Write that down. Mass of the meter stick, 70 grams. Mass of the meter stick, 70 grams. All right, it's uniform. It's a pretty new meter stick. So apart from this tiny little hole here, it's uniform, okay? So pretend the hole's not there, all right? So what I'm going to do is I'm going to grab a couple masses, and hold on, let's see, I have to make sure that I do this the way that I set it up in my notes, which are in this binder over here. Okay, so what I'm going to do is I'm going to take a 200 gram mass and hang it from the 30 centimeter mark. And I'm going to take a 100 gram mass and I'm going to hang it from the 80 centimeter mark. Now, keeping in mind that the stick itself also has mass, where's the center of mass of the mass meter stick system? Okay, so once again, I have 200 grams hanging at the 30 centimeter mark, 200 grams hanging at the 30 centimeter mark, and 100 grams hanging at the 80 centimeter mark. the whole stick is 70 grams. See if you can figure out where it's going to bounce. In other words, where is the center of mass? Okay. If you have no idea where to start, you can treat the meter stick as a particle. You can treat the meter stick as a particle. Think about where that particle would be located. And you can treat each of the two masses as a particle. So from there, it just becomes a simple calculation. Give me a minute. A couple people still calculating. You okay?
I'm tired.
You're defending yourself. You look like you're defending yourself against Jack. All right, we only got about 4 minutes, so I'm gonna go over this now. I know a couple of you are still calculating. All right, so the reason I chose a meter stick is because it gives you an obvious setup for position, right? Here's a position of 0. Here's a position of 30. Here's a position of 50. Here's a position of 80, right? It's a number line, right? Okay, so, but we've got 3 particles that we need to consider. The 200 gram mass is at a position of 30. The 100 gram mass is at a position of 80, and the meter stick is at a position of 50. Good. Why 50? Because it's symmetric. So it's the center of mass of the meter stick lies at the literal center of the meter stick because it's symmetric, right? So to find my center of mass, I'm going to average those 3 particles. So I'm going to take the mass of the 100 times the position of the 100 plus the mass of the 200 times the position of the 200 plus the mass of the stick times the position of the stick all over our total mass. Sorry?
What was that?
What's wrong?
Nothing.
All right, now, are you worried about converting? Oh, you use 20 instead of 200? I got you. All right, now, it turns out, does it matter what units I measure my mass in? No, because they're going to cancel, right? Okay? As long as I'm consistent and use always the same units for mass, I'm good. Same for position. Okay? So, here we go. The mass of the 100 is 100 grams. Position of the 100 was what? 30? 30 centimeters, right? Plus 200 grams, bear with me, times 80 centimeters, plus 70 grams, times 50 centimeters.
Wait.
Did I flip them?
The 200's at 30.
Thank you. Sorry. 200, 100. Thank you for catching that. Okay, and then divided by 370, right? Good? So if you do this, you get, what is it, 47.3? All right, hold on. How can we check it? See if it balances, right? So I'm going to have this little slider thingy. I'm going to put it at 47.3. It balances. Oops.
It's the whole.
Well, there's a cool hole on the other side. Oh, the hole. Oh, I got you. Right, I got you. Okay, but yeah, let me-
You have to drill a hole in the other side.
Did my thing slow?
Did you hold both ends?
We must have miscalculated.
There we go. Cool? All right.
It's
Anyway,
definitely air.
questions? Why does that not work? I did this before class. It totally works.
Maybe the, is it possible that the weights are like
This one has tape on it. That probably does. All right. So, real quick, spells can ring here in a minute. We are really tight on time this chapter, you guys, so we're not going to have quite as many sort of question and answer days. So Friday for sure will be a Q&A day. At the very least, plan to have this first homework assignment done by Friday, the 8182 assignment. Tomorrow we should hopefully get through all of the 8384 notes. So tentatively we'll be able to answer questions on that too, all right? We're still on our test every 2 week schedule, all right? So next Friday. So if you're struggling around before and after school, you want to see your midterm Thursday before school. Gotcha. Yes, that is fine. Will you remind me early next week about the right test? Yes.
So I was working on the lab last night. I had some issues, so I can't be willing to work out. I asked if you know
That's good.
it wasn't that much. It was like I thought like. I did the best I could. This is the best we got. So this is the original after the computer. So I interviewed everything. I got the boss again.
Alright, why don't you just walk me there now?
You did what to get from here?
Sorry, take to the jury.
Okay. It's what you did.
I noticed it.
Okay. Cool.
And I wrote a brand new conclusion and do you want an error analysis? Do you want me to email those to you, or we'll email you the document?
Tomorrow.
Oh, so
at this point.
you want the physical copy? I can go bring it off right now and
Great.
come back. I'll be back.
Okay. Sounds good. Thanks. Hey, oh, you're here for your test, right? Midterm, right? Okay. Cool. You guys good?
Yeah.
Cool.
What grades you do tomorrow? You want to give me an A for the semester?
I just a scoreboard. At this point, I got you. Where are you at? What is your grade right now? How many do you know off the top of my
I
head?
had a B first semester, A minus second semester, and then a B on the final. So I had like a B plus.
So whether or not you're a low or high, let's say it's A in my case, doesn't matter, it's just the fact you have A.
Yeah, and I just learned that on Friday. The way Pinnacle does it, it literally averages the letter grades instead of your percents.
That works for me.
Gotcha. Do you guys feel like grades are fair?
Yeah.
Inflated a little bit, but
Apparently I must have bombed that midterm, because everyone I talked to got an A, and I was like, me and Adam Scallon are like...
everybody got an A or B. I think it was about 50-50.
Really?
Yeah.
Well, I guess I'm just friends with a bunch of smart people.
I gotcha.
Go!
Okay, so you need your test. You're giving me these. This is an extra, and I can only give you 2. Is that okay? All right. Let me dig up a midterm for you. Do you have any last minute questions or anything? Okay. Give me 1 second. Sorry. Here is an equation sheet for you. You can write your name on it. Here is, I think, yes, a copy of the printer. And, oh, wait a minute. Oh, I already set it aside for you. Right here. Full sheet, printer. Cool. Oh, I didn't know you could do it. Let's see. Is there an equation sheet in here? Yes. Okay, there you go. There is one free response question on the back of the bubble sheet, so don't forget to do it. And good luck, holler if you need it clarified. You are here to give me tissues.
Yes.
I am here to put your grade in. I am also here to hit pause. Boom.